Now in the last section, I briefly mentioned that there was a method called filter that took an RDD and turned it into another RDD. That was an example of a transformation. That's one of the key kinds of operations that we can perform on an RDD. Now, a transformation always takes an RDD as its input and returns an RDD as its output. It never modifies the input RDD. RDDs are immutable, so it can't modify it. But it applies some kind of processing and creates a new RDD. The new one might be bigger, it might be smaller, it might be the same size, and it's going to be altered in some way based on the semantics of the transformation. Let's take a look at a few common transformations. I know I've talked about what they are, but I want to give you some examples of some real Spark API calls and just talk through what they do. We're only going to look at a few. I will not drag you through the whole API here, but to help flesh out this concept, let's take a look at the slide. The filter transformation, which we already looked at, creates a new RDD by selecting only certain elements out of the source RDD based on the return value of a function. Now that function gets the record of the source RDD passed into it. You get to make some decision based on that record and determine whether it should make it into the output RDD or not. Map transforms the elements of the source RDD. Each one is passed to the function that you pass to map, and that function gets to make some decision. What am I going to do? Am I going to alter fields? Am I going to select certain fields? It gets to transform the data in the source RDD to the destination RDD. There's always a one-to-one correspondence between the data in the source and the data in the destination. Now, flatMap is similar, except it kind of anticipates that it might need to break up the elements of the source RDD into multiple elements on the back end. Now, suppose the source contained a line of text. Well, flatMap would be able to tokenize that text and return now a collection of elements. So there is a one-to-many relationship from the source RDD to the output RDD. So flatMap is like map, except it anticipates that it's going to break up the element of the input RDD into multiple elements in the output RDD. So it returns a sequence or a collection of things, as if maybe you're tokenizing words on white space in a line of text. Your input RDD has a line, and you're returning a sequence of words out of flatMap. Distinct is pretty simple. If the input RDD elements are comparable to one another, then distinct will return only unique elements. So if there were duplicates on the input RDD, the output RDD will have a smaller cardinality. Sample is kind of cool. This is nice if you have really big data and you need a statistical sample. You can indicate what fraction of the source RDD you'd like to see, and even provide a seed if you want that sampling to look differently. You can seed that with the time or some other nonce that you've got lying around. Those were all unary transformations, all of which take a single RDD, apply some logic, and output another RDD. Binary transformations take two RDDs as input and return another RDD as output. Let's take a look at a few examples: union, intersection, subtract, and cartesian. Now, union creates a new RDD containing the union of the elements from the source and the other, with duplicates being allowed. Intersection returns all of the elements that are in the source RDD and the other RDD, with duplicates being eliminated. Subtract returns a new RDD containing all of the elements of the source RDD that are not in the other RDD. Finally, Cartesian creates the Cartesian product of the source RDD and the other RDD. So the output RDD is going to have a cardinality much larger than the inputs, but this is potentially useful, and later on, when we look at pair RDDs, we'll actually use this in an example. Okay, now let me show you filter, map, distinct, flatMap, and Cartesian with some actual code. We're going to start with this data. This again is our list of movies, a little bit enhanced to make it a little bit more interesting. It's a collection of strings, and it's got 7 strings in it, which are comma delimited, title, comma, release year, film data. Now let's filter that data. We played with this earlier, but I want to show you a little bit more practically how this works. And by the way, if you've got a Spark shell available running in DataStax Enterprise Community Edition, please type this code along. It'll help you a lot just to get your fingers on the keyboard. Now what we're doing is we're looking for movies from 2010. Now there are a couple different ways to do this. That technique on the top assumes that the last 4 characters of the RDD are going to be an integer, and that's going to be the release year. Probably a slightly more robust but computationally less efficient way to do that is the second example. There we are filtering movies again, where we split on a comma, take the last element of that sequence, trim it, convert it to an integer, and away we go. Now, we could imagine this movie database could get a little more sophisticated. Like maybe we want to apply some genres to it. Now, doing that for real in a real movie database or a large database of videos, well, that's a major content problem. And people are going to have to tag the movies and make decisions about what they are. Here, we're going to do something a little simpler because we're just getting started. Take a look at the code. We take the Movies 2010 RDD that we just created in the last step, and we map it. And that map method takes an anonymous function that we pass in the RDD element into it. What we do is we take that RDD element and turn it into a tuple containing itself and a set of family and animation. In other words, we're adding the family and animation tags to every single movie in our 2-movie RDD. And you can see in the table on the right now, the results that we get. We get a string and a set of strings. It's the beginnings of a movie schema. This is going to get a lot more realistic later on, don't worry. flatMap and distinct. Let's look at these examples. We'll take family movies that we created in just the last step and flatMap it. Now, the input to that function, the input parameters, will be a tuple of the movie string, that combined title and year string, and the second element of the tuple is going to be the set. All right, that's basically, think of that as the 2 columns in the RDD. What we're going to do with those in the mapping is really just pluck out that second one, the genre field. So that intermediate RDD that we create after flatMap is shown in the diagram there. That is a list of family, animation, family, and animation duplicates in that middle intermediate RDD. Then we call distinct on that RDD, and of course, as you can see, we get only family and animation as the final output. Now let's take that tiny little family genres RDD that we created, it's got just 2 things in it, and apply the Cartesian transformation on it. It's nice, if you're going to play with Cartesian, to start with a small RDD so you don't get into any trouble. Let's look at the code. We take family genres on that top line, call Cartesian with itself. We are crossing it with itself. Now I could cross it with some other RDD, but here this is the product of family genres with family genres. That intermediate RDD we then filter to produce only those elements where the 2 genres are not the same. So family is a valid part of the Cartesian product of our family genres table, but it's not very interesting. We just want to know the different combinations of tags, not where they would all be the same. So this would be, in real life, a good way of saying what sorts of tags coexist with one another in unique ways. Fortunately, in our data set, we get a pretty small combination, but the code would be the same if the problem domain were a little bit bigger.